Here we'll consider an example of swinging pendulum, but instead of bringing a new element, we will actually combine two previous examples. So we're going to have a 2.0 kilogram bob attached to a string that is 1.0 meters long. It is pulled to the side 0.5 so that it's 0.5 meters above its lowest position, and it's released. As it swings back and forth, the question will be what is the tension in the string when the bob is at the lowest position. So the combination here will be, first we'll use the energy conservation for the swinging part to determine what the speed at the very bottom of the pendulum is. And once we know the speed at the very bottom, we'll combine our results with the example from the dynamics of circular motion. Let's start with the energy first. We will need the ground. Let's mark the ground. The natural choice for ground will be the lowest position of the pendulum. That means it starts at height 0.5 meters originally. The energy at the high location will be E top, here marked, kinetic plus potential, equal to 1/2 mv squared plus mgh. Here V is the speed at the top and h is the vertical elevation at that location. Now, given that the pendulum is released from that position, that implies that the speed at that location is 0, and so we have for the total mechanical energy simply being equal to mgh. For the bottom location, kinetic plus potential gives us 1/2 mv squared plus mgh. Here the speed and h correspond to the values at the lowest position of the pendulum. But at the lowest position of the pendulum, h is 0 because we chose that to be our ground. So we can see that the total mechanical energy there will be simply equal to the kinetic 1/2 mv squared. The conservation of energy here, of course, will give us that the energy at the top has to be equal to the energy at the bottom, or mgh has to be 1/2 of mv squared. This v here is the speed of the pendulum at the bottom, at the lowest location. Mass will cancel, and we can see here that the speed with which the pendulum will be passing its lowest position will be 3.13 meters per second. So let's mark that speed. We know it's going to be swinging back on its way to the left with a speed of 3.13, and we can focus on the actual question here of the problem. What is the tension at that lowest position? That example was solved in the section of dynamics of circular motion, so you can refer to it if you don't remember it. I will repeat the steps here. We are going to draw a free body diagram here, starting by marking the vectors for the forces applied on the bob at its lowest position. First vector here is gravity, accounting for the force of gravity, mg downwards, and then we're going to have a vector upward to account for the force of tension in the rope. Let's mark also that we're going to have a centripetal acceleration, and when the bob is at the lowest position at the bottom, the acceleration pointing always towards the center of the circle will be actually pointing up at that location only. Applying Newton's second law, which tells us that the net force will be equal to mass times the acceleration, and here remembering that the acceleration has to be the centripetal acceleration, v squared over r, we can actually write the equation for the vertical components of the forces. Well, there are no other components, so that makes it very easy. In the vertical direction, the force of tension will have a positive component, so I'll mark it as plus t. The gravity pointing down will have a negative component, I'll mark it as minus mg. Here I have chosen up to be my positive direction. And that will be the total vertical component of the net force, so that has to be equal to m times a. Of course, a is the centripetal acceleration here, v squared over r. So I can see here directly that the tension in the rope has to be equal to the gravitational force mg plus an extra term that is mv squared over r. You can think of this result from this perspective. At the lowest position, the tension has to withstand the pull of gravity, and in addition has to pull harder to impart that necessary acceleration to the bob, so that the bob can actually continue moving along the circular arc. With the numerical values from the problem, we're going to have for mg 2 kilograms times 9.8 meters per second squared plus 2.0 kilograms, the speed which we actually found in the previous step, the previous part of the problem, 3.13 0.13 meters per second. Everything here is squared divided by the radius of the circle, which in this case is equal to the length of the string, 1 meter, which gives us for the value for the tension in the string when the bob is at the lowest position to be 39.2 newtons. Please remember this result is correct only for the lowest position. At any other position, the tension in the string will be different.